So we have a big topic today, and that is going to be acid-base theory. So we'll talk about basically everything. The different acids and bases, what conjugate acids and bases are, all the different calculations for acid bases, pH, pOH, pKa, Ka, everything. Titrations, buffers, you get the point. So the first thing we'll just talk about are the definitions of the different types of acids and bases. And we'll just try to speed through this, but also kind of give enough information to cover it well. So an arrhenius acid is just going to be some kind of substance that when added to water results in H+ ions. So all that's going to happen, I can just take some kind of solution, take an arrhenius, that's too small, taking our arrhenius acid, definitely not drawn to scale, and after I throw it in, now my solution has more H+. And this is definitely true for arrhenius bases, and this is definitely one of the main differences between arrhenius and Bronsted-Lowry and Lewis. Arrhenius acids really look at the macro scale, so I'm not looking at an individual molecule too much as I'm looking at the overall solution. What happens in that solution when I add this arrhenius acid? The result is an increase in H+ ions in solution. Now, on the flip side, arrhenius bases. So when added to water, an arrhenius base will result in OH- ions, also called hydroxide ions. So the flip side for arrhenius bases are true. I add them to water. I now have a higher concentration of OH- ions. So now for Bronsted-Lowry acids, we'll define them. We'll define both Bronsted-Lowry and Lewis, and then we'll get into an example of how to tell the difference. So a Bronsted-Lowry acid, a molecule that donates a proton or donates an H+ ion, a molecule that accepts a proton is a Bronsted-Lowry base. That'll be changed. A Lewis acid is a molecule that accepts a lone pair. And then a Lewis base is a molecule that donates a lone pair. So it sounds kind of strange when we talk about Lewis acids and we say accepts a lone pair, while Bronsted-Lowry acids donate a proton, but there is a definite difference here. And to talk about that difference, we'll just use this example. So we have an OH-, and then we have a hydroxide ion, and then we have a hydronium ion. So let's say that we have an acid-base reaction. And so what is the actual mechanism? What is the process for how an acid-base reaction happens? Well, a base is going to donate a lone pair. And so this lone pair that we've shown in red is going to come out and grab this hydrogen. And so what's going to happen is hydrogen only likes to have one bond. So as soon as I commit these electrons into a covalent bond with this hydrogen, that hydrogen is going to lose its electrons. And those electrons are going to go back to the oxygen. So a very important point here is this is called a deprotonation, right? I'm grabbing a proton. And a proton if you don't know, is just like hydrogen, where hydrogen is a single neutron inside of a nucleus that has one electron in the electron shell, but the difference is a proton has lost that electron. So this is H+. It is just a proton. And that's all that hydrogen is if it loses that electron. So when I say I deprotonate something and I'm grabbing just the proton, those electrons have to go somewhere. And so those electrons go back to the element that's attached to the hydrogen. So if we know this process, and now we'll draw out what the products look like. We'll have an hydrogen bound to an oxygen. That oxygen had 2 electrons, but to form a bond to hydrogen, it's going to share electrons. One of those electrons is now going to be basically given to the hydrogen. So I'll just draw that real fast. There is my 2 electrons that were originally both oxygens. Now one's been given to the hydrogen. And as I give that electron to hydrogen, that negative charge on oxygen becomes neutral. So that oxygen is neutral. The hydronium ion, that was H3O+, just lost an H, so H2O+, but that H was a proton. It was a positively charged molecule. So as this electron here goes back to the oxygen, that positive charge is now going to be a neutral charge. So that'll just be OH. So 2 H2O molecules. I just drew them differently. So what is the Bronsted-Lowry acid base and what is the Lewis acid acid base? Well, let's write the Lewis acids in blue. So Lewis acid, or Lewis base, Lewis acid, you know. And we'll write the, what color? Let's go purple. And purple would be the Bronsted-Lowrys. So, what did we say our definition was for Lewis acid? A molecule that accepts a lone pair. Well, what accepts a lone pair? Well, this molecule did, or I should just say this molecule because this is all one molecule right now. This accepted that lone pair from hydrogen as it was deprotonated. So, this will be my Lewis acid. And what donated the lone pair? That would be my Lewis base, and that was the OH minus. So what is my Bronsted-Lowry acid? I don't want to write that. Well, my Bronsted-Lowry acid is going to be what donated a proton. So what donated a proton? Again, this molecule. So this is my Bronsted-Lowry acid, and this that accepted the proton. I used different shades of purple. This is my Bronsted-Lowry base. So they kind of match up here. Bronsted-Lowry base, Lewis base, Bronsted-Lowry acid, Lewis acid. Just know the different definitions. Bronsted is about protons, Lewis is about electron pairs. So, what does this mean? Well, we can see that there's a very strict definition for, like, let's say Bronsted-Lowry, and there's a little bit looser of a definition for the Lewis acids. Not every single reaction that involves accepting a proton pair is going to be in a Bronsted-Lowry reaction. And so, what do I mean by this? Let's say we have a reaction that is a Lewis acid that reacts, but not Bronsted-Lowry. I'm going to start shortening that to BL. An example of this would be nitrogen with a lone pair. So there it is. We have something that can donate a lone pair. And then let's say we have boron with 3 hydrogens. Boron, even though you can't really see it too well, that boron can actually accept lone pairs. Boron doesn't have an octet, so I can actually give this lone pair over to boron and form a bond. And while I'm doing an electron transfer, or I'm donating an electron pair with that nitrogen, I'm not actually donating that electron pair to a hydrogen. So this isn't a Bronsted-Lowry, this would be specifically a Lewis acid-base reaction. Now, Lewis acid is a little bit more vague than Bronsted-Lowry, but Bronsted-Lowry is a little bit more vague than Arrhenius. So we can have a Bronsted-Lowry reaction that's not in Arrhenius. That sounds proper. And so an example of that would be what happens if I took NaNH2 and I threw it into solution. Well, that NaNH2 would turn into Na plus and NH2 minus. And those NH2 minuses could react, as they are a strong base with that negative charge, they could react and pick up a proton. And so if they pick up a proton, that would be an example of a Bronsted-Lowry base reaction. This would be my Bl base. But Arrhenius is specifically revolving around H plus ions and OH minus ions. So because this was put into solution and it didn't yield OH minus ions, this is not an Arrhenius base. So there is my hierarchy. Arrhenius is a little bit more strict in definition than Bronsted-Lowry, and my Bronsted-Lowry is a little bit more strict in definition than Lewis acids and bases. So all Bronsted-Lowry acids and bases are Lewis acids and bases, but not all Lewis acids and bases are Bronsted-Lowry acids and bases. So now we'll get into the properties of acids and bases.